Hello, everyone. I'm really happy to be here with you. I'm going to say just a few words about myself so that you know a few things about from where I do talk to you about that. So I was trained as an engineer, and then I went into the rabbit hole of network stuff. That was really at the beginning of this craze, at the beginning of the network science stuff. And then as an engineer, I went to work with a sociologist of migrations, and in that frame, Gephi was born. And after that, I went to work kind of as half an engineer, half a researcher to the Sciences Po Media Lab with Latour, where I kind of learned more about STS and controversy mapping and stuff. And then, after all that time, which means like 4 years ago only, I went to Denmark, where I am now, in Copenhagen, and I did a PhD about visual network analysis. And a lot of the things I'm going to show today come from that PhD. And I defended it last year. And now I'm in this lab doing techno-anthropology, so science and technology studies, which is in many ways adjacent to digital humanities and also digital methods, if you see that as a field. It could be also media studies if you want. So I am a tool maker. I'm also a practitioner, which means I use the tools that I develop. I do network analysis myself. And I'm also looking at the practices of other people like you, as an anthropologist, kind of. My screen is, the cable is kind of shaky. I'm gonna try to fix that. Yeah, I'm assuming if I don't move then, it's gonna work well enough. Else I'm gonna ask for an adapter. If someone has a USB-C adapter for, else I can also send the PDF on the other computer. If we have an issue, we can fix it. Let's assume it's not gonna cause any trouble anymore. So, some of you use the sticker visual network analysis, and I'm going to talk about that. But network analysis at large and whatever we do with networks is many different things, and they are all legit. Even what network means different things, and they are all equally valid, or maybe not all. But there are many ways to understand and to work with networks that are different. And although I will kind of prioritize one that is the most natural to me, I'm not in any way saying that the other ones are not good to use. And I'm going to kind of clarify, that's kind of my goal here. One of my goals is to clarify the situation, what is network analysis in different contexts and so on. So that's why I also have the word social network analysis. The other big sticker that you will hear about, that you know about, is social network analysis. And even that means different things. That's what we are going to talk about today with the angle of the humanities. So for the sake of brevity in my slides, I'm going to use a few of those acronyms. I'm going to show you them now. NA means network analysis, and then if you have a V, it's visual network analysis. If you have an S, it's social network analysis. And I will also briefly use network science, which is NS. And this is my plan. I have like 7 sections. I'm going to start with showing a little bit of visual network analysis, also showing a little bit of social network analysis. Then I'm going to engage with this question of what are the different fields that use networks and how to differentiate them and how they also overlap and how to get oriented in that. Then I'm going to explain what VNA is in case you need some clarification, and I have a few things to say. Basically, it's just network analysis with picture. But with the pictures come problems, so that's what we need to talk about. One of the biggest problems is the layout, so where the nodes, where the dots of the picture are placed. I need to talk about that, so I will unpack this because it uses an algorithm. And then I'm going to engage with how you can read the layout, what you should know to understand how it goes. And I'm going to finish with a few guidelines and reflections about what happens when you share a network map you have done, either in a paper or on the social media, for instance. Okay. Let's talk about what is visual network analysis, and I'm going to show you an example. It's kind of typical. I don't know if there is kind of a typical way to do that, but that's the most recent example from my work. And I'm going to use that as a way to, broadly speaking, characterize what is visual network analysis. So this is a map. What you see is a picture of a big printed map that we have annotated manually. And it's a map about what AI algorithms and machine learning do within science. Just before I explain a little bit more, now that you've seen this image, if you can make a mental note of the effect it produces on you, like what do you think it is, that what it evokes to you? If you can just fixate that now, I will come back to what those images do at the end of the presentation, right? Okay, so this is a big network of keywords. So what we have done is, this is the same network in Gephi. So just if you don't know what a network is, I assume you do, but for the sake of clarity, the language we use usually to talk about networks, and that I'm going to use too, is nodes are the little dots that represent an entity, and edges are the connections, often represented by a line or a curve, that connect these nodes together, and they are the relations. If you don't have relations, you don't have a network, you would not do network analysis. The reason you would go to these technologies or methods is because you are interested in the relations, right? So here it's a network of many words or expressions that we have extracted from 1 million paper abstracts from Scopus that contain either the word algorithm, machine learning, or artificial intelligence, and the different variations of those words. So there is kind of a quantitative preparation step to this map. We downloaded these abstracts, we extracted the named entities and the n-grams, we partially curated it manually to ensure a good coverage and so on. And then we made a co-occurrence network. So two words are connected when they appear a lot within the same document together. There is a certain way to weight the edges so that it works. We use point-wise mutual information. You can forget about that. I don't want to talk too much about this process. We can talk about it if you have questions later on. But basically, we have a lot of little clusters that are words that go together because they appear together in the same documents. You could think of them as fields if you want. So one of the questions is that what are these fields or topics or points of interest? I don't know how to characterize them precisely. And how are they related to each other, right? Knowing that it's not all science, it's just the science that is about algorithms or makes use of algorithms, AI, and machine learning. So what we do is that we have printed this on a big paper sheet, and we do annotate it manually with pens, right? So we have highlighters and stuff. And what we actually do is, first we want to understand what are these clusters. So we'll go back to the abstract from the words. So let me give you here an example. So in black behind you have the base map, the network as we printed it. It has a few words that you can read. You can read prefrontal, cortex, psychiatric, whole brain, right? So we can look at these words, search for the abstracts, look at the abstracts, and we ask ourselves, how are algorithms involved, and what do they do, and what are the commonalities between those papers? And then we have a kind of one paragraph of description of that we reduce to one short label because we do not have enough room for more. And that's what we mark as a landmark here. So we make a red cross when this area around the landmark is, broadly speaking, about, in this case, analyzing brain imagery. So algorithms are used to analyze brain imagery. And then we have two other kind of subclusters or adjacent clusters. One is about mental health and one is about brain science. So we have something like 250 of those landmarks, and then we have about 50 bridges because sometimes the connections themselves are interesting, so that's why we also have these orange highlights. Right? So for instance, here we have a cluster that is about algorithms in social sciences, and then we have a cluster that is about algorithms in audio things, so where you had music genre recognition and application to cochlear implants. And they are connected through this bridge that we marked as language, because if you do machine learning on language, you can connect both to spoken languages with words such as speaker, but also written language, and that's where you would have words like sentences. So there's a cluster joining the two. There's a set of papers that is both about the audio and the written language, right? So we have these kind of bridges everywhere. I mean, not everywhere, but in many places. And that's what we are interested in. Sometimes it's complicated, so we had to kind of bend the bridges in some ways, and like you have here a very complicated area of the map. Yeah. I'm not going to do the whole visit of the thing. It doesn't land on findings at the stage we are in. So let me just say, you've seen the kind of things we do. What can we get from that? So we don't get any clear answers. Like, it's not a top-down methodology where we had hypotheses that we tested. You know, we did that, and we want to explore that, and then we'll do other things later on. So at this stage, no findings. It doesn't provide answers, but it provides questions, and we have an excess of questions. It's very descriptive, right? We describe and we make more clear a number of things in the structure of this network. It's about clusters and bridges. It requires qualitative knowledge. So we go to read the abstracts, but we will also, with this map, go to see experts of the different fields that we are not experts of. Where we can kind of delineate social science, but when it's health or energy or other fields that we don't know that much, we have to get some additional knowledge to understand that. So it requires qualitative knowledge. It can allow other people to engage with it. So you can go with the map, ask someone if they understand certain areas. So it can be used as an elicitation device. And it's just one part of a larger research design that I'm not going to explain here, but you know, we had done some things before analyzing the network visually, and we will do other things after that. It never works in isolation, I think. Good. Now, for the sake of contrast, I want to talk about social network analysis and give kind of a typical. Once again, is it really typical? I don't know. It's really hard to. I'm not here to say what is typical in social network analysis, but at least I'm going to take a classic, a very largely cited paper by Mark Granovetter. You all know the strength of weak ties. Do I need to explain the strength of weak ties? Is it okay, or I'm going to move on then, because this is not the paper I want to talk about. Everyone knows, so Mark Granovetter. The strength of weak ties is 73, cited like 67,000 times according to Google Scholar. The one I want to talk about is almost as cited, 50,000 times. It's more recent. It's a chapter in a book published for the first time in 1992, re-edited in 2011, so kind of recent. And the book is The Sociology of Economic Life, and the name of the article is Economic Action and Social Structure, the Problem of Embeddedness. And let's start by, I'm not going to unpack completely the paper, but let's start with the first sentence of the chapter. So Granovetter writes, how behavior institutions are affected by social relations is one of the classic questions of social theory. Right, so although we have network, the word in visual network analysis and in social network analysis, what you have seen from what I do is not really, you could see that as sociology, but it's not really about social theory. Well, for Granovetter, this is all about social relations and social theory. Right? This paper has no table, no picture. It's just text. And still, it's really representative of what social network analysis can be. So basically, the point of Granovetter is that he wants to advocate to his peers, to other scientists out there, that the actors studied do not behave or decide as atoms outside of a social context, which he called under-socialized conceptions, and they do not either adhere slavishly to a script written for them by the particular intersection of social categories that they happen to occupy, which he called over-socializing conceptions, right? So that's the point of the paper. That's what he says in the paper, in the chapter. And in the part of this chapter, he clarifies what networks is for him. So he writes, the embeddedness argument stresses instead the role of concrete personal relations and structures or networks. So this is what networks are for him. Concrete personal relations and structures. The networks are not nodes and edges. They are us human beings being in relations to each other through direct contact, but also many other things like how we trust each other, how we are embedded in other social structures like, I don't know, our work, our country, our family, all of that. Yeah. So you can see that the two are very different. We need to talk about that. That's my section now. And I'm going to start, before coming back to SNA and network and visual network analysis, I'm going to start with the outlier, but I need to talk about it. We've seen that yesterday. ANT, so actor network theory, right? The STS methodology. I'm going to start with the dissertation from Bruno Latour, who is one of the creators of the ANT. And this is from Reassembling the Social. It's a kind of a dialogue that he would have been with a student at the London School of Economics, he says. So he explains you should not confuse the network that is drawn by the description and the network that is used to make the description. The student is puzzled by this sentence, maybe you are too, and he says, but surely you would agree that drawing a pencil is not the same thing as drawing with a pencil is not the same thing as drawing the shape of a pencil, right? So the pencil that you use as a tool is not the same as the pencil you would draw. And for him, ANT is not studying networks. It's using networks as a mental framework, as a methodology to study things that may very well not look like networks in everyday life. Right? So my example yesterday was Ukraine. I say that because the reason why Latour would do these kind of things is he wants to show the work that is making the things last or maintain themselves into existence, right? So you could, if you assume that Ukraine exists, you cannot understand what people are doing right now in the war because they are trying to maintain Ukraine into existence or a certain form of Ukraine. If you want to see that work and understanding, if you want to unpack it, it might be useful to see the relations everyone have that are, so you would say Ukraine is a network. So that's the core idea of ANT, is any actor, anything that acts is an actor or an actant, if you prefer. And then every actor is also a network, and every network is also an actor. It doesn't mean that they are, it means that you may want to see them as networks if you want to study them with certain research questions, right? We have written a paper with Tommaso Venturini and Anna Smunk in this book that is in open access. You can read this article, where we explain the difference more in depth between actor network theory and network analysis. But for Latour, like for instance, if you read one of the main papers of ANT, which is the Calon's paper about the scallops in the bay of the Mont Saint-Michel, he draws pictures, but they are never pictures of networks, even though for him, he talks about it in the form of a network. So it's not network in the sense of nodes and edges either. So it's a tool, but it's not nodes and edges. So this one is an outlier. And then we have the three other fields that are strongly overlapping, which are network science, social network analysis, and network analysis. And there is very real overlap. So let's talk about that with your compadre, Albert Laszlo Barabashi. I don't know how, I probably don't pronounce his name very well. At the end of the 90s, starts this new scientific program at large called Network Science. Katie Berner says about it is a highly interdisciplinary research area. I think it's appropriate. You can see it as a field, but it's subject to debate. The main object is the complex network. So it's very interested in complex systems too. And it roots in graph theory. It's very mathematical. Statistical physicists like Barabashi have had a very huge influence on that. And the theories of network science have disseminated as an operational toolkit to other fields. So in particular, a lot of the empirical networks you may find during your work. So for instance, the network of words from science that I have shown you, this is a complex network in the general sense of having a distribution of the degree that follows, roughly speaking, a power law. I'm not really interested in the modeling, so I don't really care. People would say it doesn't really follow power law, it follows a heavy tail distribution. I'm just mentioning that there is a controversy about complex networks and the role of Barabashi. I'm going to leave that aside. But complex networks is important because it's kind of the type of networks you always find, or most of the time you find when you have empirical data. And you have a few nodes that are super connected and many nodes that are not very connected, and this creates problems. If you want to solve them, you may want to draw from the findings of network science. So it's really useful in that sense. Now, the other elephant in the room is social network analysis, and you may not know about that, but it's much older than network science, right? It's the actual original field where network analysis was born, for the simple reasons that the math that will lead to network science don't really look into empirical data, while social network analysis has done since a very long time, at least since the 30s. And, well, so as you have seen from Granovetter, you can understand social network analysis as the analysis of social networks. So social networks is the name given to the phenomenon that we are in relation with each other, right? So the phenomenon takes the name network and you analyze it, and you may analyze it, worst case scenario, not even as a network. But usually you would go to that field because you are interested in the network nature of our relations, but the questions of how you datafy the phenomenon of the relations into nodes and edges is always problematic, always discussed, always scrutinized. You know, the people in SNA do not believe that our relations are like lines that connect us. They don't boil down to Facebook friendship, Twitter retweets, phone calls, emails. They use all of that, but those relations are never what they call the social network. The social network is the unknowable, mysterious, thick relations we have with each other. So this is very, very empirical. It uses network analysis. One of the oldest example is from the 30s, Jacob Moreno. So let me just unpack that super quick, and I will come back to it later on. These are two groups of kids. He's just going to the kids in the classroom. He asks them, who would you like to sit next to if you could choose? So that's a way they disclose their friendships, acquaintances. So he uses that as a relation. Then he draws the boys as triangles, the girls as circles. He knows already, we are in the 30s, he has no computer, obviously, but he already understands that depending on how you place the nodes in the space, you see different things. He places the boys on the left, the girls on the right, and you see immediately that the boys want to sit next to boys and the girls next to girls. Only one boy wants to sit next to a girl, or vice versa, right? So this is the first case of visual network analysis, if you want. It's very empirical. It's also a small network, which is important. We'll come back to that. So network analysis is, on the contrary, network in network analysis means nodes and edges. It's first and foremost, it's a practice. It's whoever uses Gephi or uses the other softwares that exist, or code, you know, like scripts and libraries like Network X or whatever, R. If you do that to analyze networks with statistics inherited from social network analysis or network science or something else, then you do network analysis. So it's kind of a practice, it's a technique, it's a methodology or a set of methodologies. It applies to many different fields. It makes no assumption on what the network of nodes and edges represents or models. It doesn't really care about it. It may not even be empirical. It might be pure graph theory. You would still possibly call that network analysis. And of course, because it's a practice, it has also become a field that is reflecting on the methodology of the practice. So are the algorithms used by people appropriate, and so on. You can find the state of the art of network analysis. They call it network analysis. And they say, yeah, they are quite honest about the fact that It's a set of techniques born in social network analysis that then radiated elsewhere. But everyone has radiated to the other techniques. I think we may have forgotten a little bit that SNA was there first and that they created stuff that went to network science and then came down to us later on and that we may perceive as coming from statistics and stuff, while it was actually born from in SNA.
So
Question? Yes?
Clearly understand the reason why isn't network analysis containing both network science and social network analysis?
So it's containing them, but it's also it also goes beyond. So for instance, if you can do network analysis of gene and proteins, then it's not social network analysis, and it might not be network science, or maybe it's also network science. But what's important is that if you have nodes and edges, then you do network analysis. And if you study something that you see as a network, but you may not use nodes and edges, then you are one of the other fields. And if you use nodes and edges to study social networks, then you are in both, or possibly in the three of them. But keep in mind that the network means at least two different things. It may mean the phenomenon that is not reduced to your nodes and edges, and it may also mean your nodes and edges. So always be aware of that reduction and what it does in the fields. Because in SNA, they certainly never make the mistake. But also it's confusing for everyone. So the most important mistake not to make is to just go to Gephi and say, now I do social network analysis. Well, what maybe you do, but you only do it insofar as you can explain how your nodes and edges relate to a social phenomenon. Or another phenomenon, like ontogenesis, if you are doing gene-protein interactions or something. Yeah. I hope I gave you a few guidelines. If so, like this, I have a longer explanation of that, both in the blog post on my blog, but also in my PhD thesis, if you need some references, especially where the people of the three different fields describe their own field and what do they say about the distinctions with the other fields. Okay, so visual network analysis is just network analysis with pictures, right? So one way to situate that is to say, well, if you have data, let's say you do data science. Data science is not just about analyzing, it may be about harvesting, cleaning your data, all that stuff, but there's a part that is analysis. Then when you analyze your data, if your data was networks, which means you had relations, then you are de facto doing network analysis, and then if you use pictures, you do visual network analysis. As I said, it's not either or. You may do visual and non-visual network analysis. I mean, it doesn't make any sense. It's just that you would not do visual network analysis if you don't at least have pictures. As I said, it's always part of a bigger whole. The same way the analysis is part of a chain where you have harvesting and stuff, the visual part is always associated, I think, most of the time with statistics and other things, or qualitative inquiries. Okay, so if I say that, then you may just ask, well, since we do have statistics about the networks, do we even see those statistics in the pictures? And that's a very good question. That's an open question. The short answer is kind of yes, kind of. Depending on the metrics, you see them more or less. The one that we see the best is the bridges, and that's the thing that we are most of the time interested in, or the clusters too, it kind of goes together. You can use betweenness centrality to identify the bridges. I think that's a really classic methodology for network analysis at large. It works with the visual and with the statistics. Now, you will compute possibly different centrality metrics. Here you have like degree centrality, page rank centrality, closeness centrality. They give you different feelings of what is central in the network. And they have different correspondences with the social theory if you go the road of social network analysis. So for instance, betweenness centrality, the bridges, you may interpret that as brokers. So nodes that if you remove them, create disconnections in the network. So they are kind of obligatory passage points. There is a social theory of that. Voilà. We have written a paper with Martin Grandjean that you may know in the field of digital humanities with a very big appendix about the correspondence of what you see as a visual pattern and the different statistics. I don't have the time to dig into that here. But let's say that it could be an entire scientific program to establish that better weights. It has not been done so far. Okay. So now I want to kind of commit to visual network analysis and explain what it entails and what you have to know. So this is a toy example that I'm going to use for a bunch of slides. Those are articles from Wikipedia. They are all about Europe, and they are connected by see also link. The hyperlinks that you have at the bottom of certain articles, they say see also, and then you have other articles. So articles connected together. And I didn't want to do anything with that, it's just an example, but you can see the typical network that would put you on the path to visual network analysis. So first of all, it's big enough that you cannot follow all of the edges. This is really important because if your network is really small, you don't have the problems that visual network analysis is solving. So you may just look at your diagram and understand it. You don't need anything. You can go fully qualitative. The problems come when your network is big enough. You will have distinct clusters. This is not a given. You may not have clusters. If you don't, visual network analysis is not going to work very well for you. You would rather go statistics fully. Visual network analysis really works when you have clusters. And we have a few highly connected nodes. You may see them, they are bigger and they have a lot of edges around them. And we have a lot of mostly poorly connected nodes, right? Those are the small ones you see around. This structure with a few super connected and many poorly connected is the signature of, let's say, complex networks. So if you are in this situation that is quite classic with empirical data, you are on the territory of visual network analysis. And what's really important to manage and understand your process is to be clear in your head about the layers of mediation that have been involved in the building of this picture, right? So in this case, so I had the empirical phenomenon I'm studying, which is Wikipedia. Right? So the articles in Wikipedia, they have images, they have, I can experience them through my browser. I am reducing them a first time to HTML code where I can extract the links. This is a first reduction. Then from that, I am extracting two lists that are the network, so the list of nodes and the list of edges. I have to make choices here. For instance, I don't take all the links, I just take the see also links. I will need to account for that later on, right? So now I have these two lists, and this is already a network. I don't need to visualize it. I could already compute it. It doesn't become a network when I make the map. It is already a network. It has its own structure. Now I will make a map to understand it empirically, right? To experience it. So I will make the distinction between two steps. The first is the layout. So I will just give coordinates to the nodes according to the edges. I will come back to the layout, but basically, the super important step here is that the position of the nodes is going to encode the structure. Because the layout places the nodes according to who they are connected with. That's really what it's doing, and that's why it's important, right? So ultimately, we could even not draw the edges. It's still useful, but the edges are there nevertheless, even if you don't display them. They are hidden in the position of the nodes. And then there is the rest of the map, the colors, the sizes, anything you could do to make it readable. The last part is just classic visualization work. It doesn't mean it's easy, but it's not that different from doing a readable pie chart, right? Or a cartography. But the layout is really specific to networks because the layout encodes the structure. So those are the layers of mediation, and if I want to explain how the articles are connected, it means I can relate the patterns that I see in the map to the empirical phenomenon through these multiple layers of mediation. You have to be able to do that if you want to write a rigorous paper. Okay, so the hard part is the layout. In this section, I want to say essentially this, so I'm going to state it up front. In the literature about graph drawing, which is the name they give to making network maps, in short, there are two different ways to, depending on what you read, which paper you look at, there are two different conceptions on what it is to read and interpret a network. The old one, inherited from the networks before the 90s, or in the 90s, is what I call the diagrammatic interpretation regime. It means you have to follow the path, and then you can do a qualitative assessment. So being readable means you can follow the path. It only works if your network is small enough. But what we have nowadays is completely different. That's what I call the topological interpretation regime. We have so many edges that we cannot follow them anyways. What we want is we look at the positions of the nodes to understand the structure. And maybe having the edges drawn is helping us, but we cannot follow the path because we have too many nodes, too many edges. So it works differently. I would like to make the whole history of that. I don't have the time, but in short, so the layout, I think you know that. We have a repulsion force and an attraction force. And it's kind of physical simulation system where it converges because the attraction force between connected nodes is like a string. So if you pull, it pulls more. So it pulls you back close. And the repulsion force is the contrary. It's like two magnets with the same polarity. It repels the nodes, but when they are close. So if you're too close, you get more far away. If you're too far away, you get more close. So of course, at some point, you stabilize in kind of the ideal position. But it's not just between each pair of nodes, it's between everyone. So that's why when you run the layout in Gephi, you would see everything moving and then stabilizing. There is what we call a minimum of energy. There is always kind of a landing position, a landing configuration for your whole system is guaranteed to be there if you have the right formulas. Now, it doesn't mean that there are different ways to implement that, so different algorithms have different results. They are kind of similar to each other, but they also have differences. The best in terms of resulting qualities, the lean log, the one here on the right, it's also a mode in the Force Atlas 2. Let's talk about the practicalities if you want after that. I think most of you have discovered that by themselves and understood that. This is all part of the craft of visual network analysis. But the principle at play is the same. Okay, so very quickly, because I don't have that much time. In the 30s, no computers. The layout is done manually by Moreno. The networks are small, and they are empirical. And what is really interesting, I think, so that's one of the things that is empirical, is that then it's going to be kind of forgotten, and then it will be reborn by looking at what people who draw diagrams in the industry, right? And from that, these are small networks too, but they are networks also in the sense of, they ask questions such as how do you draw the boxes, how do you put the labels? The nodes are kind of, they can have different shapes and whole trajectories. This is kind of not really how we conceive networks for ourselves here today. And from that, they are going to extract some aesthetic criteria that will become the foundation of the diagrammatic understanding of networks. And those networks, so here they are they are not empirical, but they represent processes, for instance, in engineering. And then you got, in the papers about algorithms or about graph drawing, you will find a lot of small networks. We are here in the beginning of the 90s. Small networks, not empirical. Now we see stuff that is geometric. I'm going to skip that. Then early 2000s, we start to have bigger networks because we have computing power, but we still have geometric networks. A lot of them come from 3D meshes. It's the beginning of the 3D for, so those are not empirical networks. And then finally, so this is the gold standard, the lean log, 2007. We are now 10 years after the beginning of network science, and now we got again, empirical networks, also big. This is kind of where we are now, right? So after all that time, we go back to having empirical networks visualized as in the 30s, so 70 years later. But now the networks are big. It had to be through non-empirical large networks to go back to empirical large networks. This is my paper for the Force Atlas 2. I also, at the time, show empirical networks. This is really important because empirical networks are not necessarily like geometric networks and stuff. Right? So the people who develop algorithms for 3D meshes, for instance, they solve problems we don't have, and they don't solve problems we have. So that's why we have the coexistence, in short, I can't tell the full story, between these two ways of thinking. One is kind of inherited from the past. The other one is more contemporary. But it's also because social network analysis was kind of forgotten in the meanwhile. Okay, so now that we know that, so how do we decode the layout? So this is kind of practical advice. I'm going to be a little bit late, but I still have to conclude that. So I'm going to draw on Gestalt theory. It explains how do you see groups, in how your cognition parses groups of items. You probably see a big square on the left and 3 bounds on the right. There is no square and there are no bounds. These are just dots, right? But depending on the proximity relations, your brain sees them as a whole or as different things. This is super important for networks because same thing, I have a bunch of dots, it's the same, and I'm just, spreading them a little bit more, and I'm kind of guessing that probably you see this one as one group, and you see the bottom one as 3 groups, and in between, well, it depends, right? So there is this ambiguity, but for us to see 3 groups, we need the gaps, which is super important because when the algorithm of the layout is spreading the nodes, it tries to put connected nodes closer, and it tries to spread out disconnected nodes, but spreading out for the algorithm is kind of from center to center, while for us, we see the groups if there is a gap border to border. So if there are big gaps, it's okay, but here, as you can see, there are no gaps border to border, so we see this bunch of nodes, we see them as a whole, but for the layout, for the computer, there are gaps, because from center to center of these 3 subgroups, there are gaps. So in the mind, I'm anthropologizing here a little bit, but it's for the sake of clarity. In the mind of the algorithm, the job is done. There are gaps, you see different groups, and you don't see them. So, because the case where you would agree, if the layout had conflated everything, the groups would really be merged together, and you would have this, basically. So on this end of the spectrum, we agree with the algorithm. On this end, we also agree. But in the middle, there is kind of cognitive mismatch between the algorithm's way of thinking and our cognition. And there's nothing we can do about it. It's not the algorithm that is right and we are wrong or vice versa. It's just we're not the same. So here is an example, empirical example. This is a planted partition model. We have 2 groups that we know, and we connect them not more and more, so the layout puts them closer and closer. And what is really interesting here is that just before the end, here in the end, this is like 50-50 chance, so there are no more groups. They would really be mixed. But before that, it's 60-40. If I don't show you the colors, it really looks the same. But if you look at the color, the layout has been very good at putting the green on the left and the purple on the right. So the position keeps making sense. In the layout, it works, but you don't see the groups because they are next to they are contiguous. When it's contiguous, you will miss them. So there is a way to, if you know that, you can see through this problem. The classic thing is that when you have subgroups glued together, it doesn't make a homogeneous ball. It gets stretched in this layout. So when you have an ellipsoid shape or elongated shape, and often it's going to be denser on the ends, it means that you probably have 2 subgroups that are also kind of connected in a bigger groups, but they are still different. And it's complicated for me to enunciate this structure, but that's just how it is. This kind of ambiguity is a feature of the data. It's not a failure of the algorithm. It's just reality is messy. Your empirical data is messy like that, and our job is to account for it when we describe it. If it's, we don't belong to just one circle. Do you belong to your family or do you belong to your friends? Obviously, it makes no sense. A little bit of both, also none, That's how the social networks are, right? And so the structures we get are ambiguous in that sense. They are intertwined and tangled. Example, this is the neural network of a small worm, a nematode. This is from the super famous Small World phenomenon paper, foundational in network science. I didn't display the edges, but they are encoded in the form of the position of the nodes, right? So maybe you don't see groups. If I run community detection, you will see groups. But now you know that basically you could have guessed where the groups are because the groups are what is stretching this structure into not a ball, but something that has corners, if you want. So the corners are where the clusters are, and in the middle, the rest is stretched between the clusters, if you will. And basically, if you run community detection, this is the algorithm that is in Gephi, modularity clustering. If you run it many times, it's going to hesitate. It's non-deterministic, so it's going to find in different configurations in the middle. But it will not hesitate on the sides. So the left corner is always red, the right corner is always purple, and the bottom corner is always green. It's only in the middle that is hesitating, right? So, which is also why these community detection algorithms are kind of problematic, and where the layout is in some ways superior, because the layout is honest about this ambiguity, while the community detection is going to give you a limit, but that limit will be fluctuating, because like, you ask a limit, it gives you a limit, but it doesn't mean that this limit is always very good. It's good for the nodes on the corners, and it's not very good in the middle. So that's how sometimes the visual is superior to the computations. Okay, last bit. I'm sorry, I'm a little bit late. But this is so important. So I've been in a seminar as a PhD student, and someone showed the slides. It was not about networks, and suddenly there was a Giphy screenshot, and the person said she didn't know I was there, and I didn't know who she was, she didn't know who I was. She said, we also do this kind of fancy visualization, and then she moved on, and I was like, what the fuck? If you don't want to show it, don't. Yeah, you pick that slide, and then if you have nothing to say about it, why put the slide? And then I thought, okay, it must do something for her, right? So that's how I came to think of it as what I call storyletting, the act of sharing these kind of visualizations and by letting the visualizations tell their own stories, right? So I think what happened is you've got a screenshot that you have taken to document your process, whatever, and then later on you have to assemble your slides, communicate, and then you're like, yeah, this screenshot seems nice. It could give me some, it could be a good communication asset. It could be nice to show that I'm also doing that, and you're going to slap it. But then it was not, the screenshot was not taken with a specific idea in mind, maybe, or you cannot explain it, so now you have to live with the inability to explain it. You're repurposing stuff. And then that's how you may put yourself in this situation, right? So, example, but there is a ton of that on Twitter. People say, okay, this is a graph of Twitter mentions over about 2 hours, whatever. Like, what can I say about that? Can we understand anything about that? What does it tell? Well, the things it actually tells is like, I do big data, I do network stuff. This is impressive. I don't know. I'm a computer scientist now. I don't know. If that person wanted us to actually understand this image, they would need to provide context. They may not have realized that, or they may have, and they just want to, get some engagement. Think of that. This is storyletting. The problem is that then you've got these images that are floating around, and it may be perceived as a threat of methodological imperialism, of network science over the digital humanities, or whatever. It may imply that you have to do that to be a real scientist. Like a lot of things that we may not want to live with, and we don't have to. Network maps can be useful and meaningful. You just have to annotate them and provide context, right? So the semiotic phenomenon at play is what I call the noema of big data visualization. I'm not going to explain what noema is. I don't have any more time. Think the essence of big data visualization. And this doesn't apply just for networks. It also works with this kind of visualization. Basically, if you look at this, first of all, there are a lot of data points, a lot of signs, and it looks like there is a pattern. If you look closely, you will maybe recognize this is Denmark. You will see bigger bars for where you have cities. So it looks like it's telling something, but you don't know what. And you can't actually know because you lack the context. But it feels like there's something to find, right? So for very legit reasons, you would get out of that there is an order to this chaos, which means quantitative opportunities or whatever it means. This is not usurpation. It's very real. The same goes for my map. Did it work for you? Do you remember the mental note I asked you to take? Did you think, wow, a lot of stuff is going on, but also, I don't know, what is this, what is that? Did you catch patterns? If you did, but I didn't at that stage, you couldn't read the map, and you probably cannot still. But still, it kind of impresses you in the sense that it really looks like there is something that would allow you to go deeper, which is true. But then this is the power of the map, and the power you have the responsibility to keep in check. So the good landmark for that is when you are in Giphy and all of that is really easy because you are in an exploratory setting, you visualize for yourself, so there is no problem. So visual network analytics is mostly exploratory. It's not about releasing network maps to the public, it's for yourself, and it's plenty enough. You can very well explore for yourself, and then when you write the paper, you don't put any visualization. You know, you have found interesting stuff that you can now grasp with a qualitative means. It's totally fine. Now, if you do communication, then you go on into explanatory visualization territory, then you need context and visualization. This is work of my students that I have revamped so that it's a little bit nice, but this is their annotations, right? I'm not going to unpack that. I don't have any more time, but basically, they write a description, there is a title, there is in-place annotation that makes a point, and the point is explained in this text. So you can, if you spend the time, you can understand what this is about. You have the means to do it. And this is not letting the map tell its own story. You tell your own story. So when you release a network map, I have a checklist. The first point is annotate, and check that you have annotated the map, at least with some text and a title, a legend, but possibly in-place annotations. And so check the layers of mediation. So I'm just going to finish with a super simple example. Super famous networks, divided day blog. In blue, the Democrats. This is just before the second Bush election after 9/11. La Dynamique, Nathalie Glantz, super famous paper. Before Giphy existed, it inspired us. The Democrats in blue, the Republicans in red, and you see kind of, they say in the paper, the polarization of the American political life. But what you have to not miss, and that's why the layers of mediation are important, is that everyone sees the blue ball and the red ball, but what's important is to understand, if you make the point, that the fact that you have two balls means you have two groups, structurally speaking, and the fact that you have two colors means you have the Republicans and the Democrats. But it's not a given that the structure, so the positions and the colors would match. And if you look closely, they don't totally. There are a few red in the blue and vice versa, right? So you may not know that. You may think that it's mapping the same thing. Then the map would make no sense. It only makes sense because they don't map the same thing. Because you could have this situation, right, with mixed colors. You don't, and that is why we see the polarization. So basically, if I unpack everything through the layers of mediation, starting from the right, so we see blue dots on the left, red dots on the right. I'm speaking image level, so shapes, right? So then I will go back to the layout. So the dots are the nodes, and the colors are the kind of nodes, political affiliation, right? But the kind of nodes, so the layout placed the nodes of the same kinds together, one kind on the left, one kind on the right. Then I can move to the network layer. So now the being placed together means being more connected. So the nodes with the political affiliation, Democrats are more connected, and the Republicans are more connected together than they are connected across. And then I could go back to the phenomenon, which is the blogs. So the people at the time when they add a link to their blog roll, this link is more often than not a link to someone that is of the same political affiliation. Now I've rigorously traversed all the layers of mediation, and that is why I can now say that we do see what is called homophily, right? The tendency to look to who is the same. Only at that price I can say that we see it, because I explain where we see it and how we see it. Well, here we are.